Okay, we're going to begin with the technical session number 1. We have 5 papers, 3 on the track ethical, humane, and sustainable applications of computational intelligence. Unfortunately, one of them is not able, is not here to make their presentations, and 2 papers from the evolutionary and swarm computation track. The first presentation, the article is name is Fire Detection Based on a Two-Dimensional Convolutionary Neural Network and Temporal Analysis. It's going to be presented by Pedro Vinicius from Universidade Federal de Minas Gerais, Brazil. You can begin your presentation.
Can you
You can share your screen.
yeah,
Or not?
I can't share my screen.
Cesar, can you allow him to?
Give me a second.
Host disable participant screen sharing. I can't share. Can the host give me permission to share?
Try now, please.
Okay, thank you. Okay. Hello, everyone. My name is Pedro Vinicius. Today, I'm going to present the paper Fire Detection based on a two-dimensional convolutional neural network and temporal analysis, written by me and my advisors during my master's degree. My presentation is divided into an introduction, proposed approach, experimental results, and conclusions with possible future work. Unsurprisingly, wildfires are becoming more frequent all over the world. According to National Intelligence Fire Center, more than 4 million hectares of land in the United States were burned in forest fires in 2020. A very similar situation has been taking place in South America over the past 2 years. According to the National Institute for Space Research in Brazil, there were 32,000 fire events in the first 3 months of this year. Therefore, it's clear that early detection approaches are necessary to avoid major losses. So computer vision-based approaches have been easily applied to fire detection problem, and they can be divided into 2 strands. The first and pioneering one is known as the top-down approach. The methods belonging to this approach consist of defining deterministic rules for identifying fire or smoke. The most common methods used color segmentation in different color space, such as RGB, ASI, and others, and also temporal analysis, such as optical flow, background subtraction techniques. However, over the years, some limitations were observed. It was difficult, for example, for this kind of strategy to generalize well to new scenarios. You define the rules to identify the fire or smoking in a given lighting, and when you change the environment, those rules no longer work. In the case of temporal analysis, these strategies still had a strong dependence on camera stabilization. If it was shaking for any reason at all, that could already hinder detection. From this perspective, the bottom-up approach emerged, which consists of learning the visual patterns of fire and smoke from the images, and later using this knowledge to identify new fire events. Unfortunately, this learning approach still resulted in many false alarms. In several studies, it was reported that fire and smoke had visual features very similar to other objects common in scenes. For example, saturate fire with car headlights or smoke with fog and clouds. Thus, we propose a fire detection system which consists of two sequentially steps. The first is the detection. This step aims to identify the fire and smoke events in the environment. For this purpose, an object detector based on a two-dimensional convolutional neural network is used. And the second and last step is the temporal analysis, which takes the detection made in the previous step and tries to verify if the detected object is in fact fire or smoke based on its behavior, temporal behavior, along the consecutive frames. In this diagram, we show that temporal analysis will be implemented as a tracker, which will visualize if the detected object spans or spreads over time. Detectors based on deep convolution networks can be categorized into two-stage detectors, whose first stage propose regions with the object of interest, and the second stage classifies these regions. And single-stage detectors, where classification and location steps are done together. These two categories of detectors deal with the trade-off between speed and performance, where two-stage detectors are typically more accurate and single-stage detectors are typically faster. In this way, we choose you only look once algorithm, a single-stage detector. It's extremely fast and is open source in C language. Yolozy is already in its 4th version, showing very promising results in other tasks. We also trained the 4th version of TinyYOLO, a simplified and faster version of YOLO. However, this higher speed comes at the cost of lower performance. As I said earlier, the proposed temporal analysis is based on object tracking. This tracking algorithm consists of a multi-step process based on the centroids of the detected objects. Let me give an example. Suppose in the top left frame, I have identified a fire and smoke event, which I number 1 and 2 respectively. In the next video frame, these objects may have moved or increased in size. To find out where they are located in this new frame, I compute the Euclidean distance from their position in the previous frame, dashed bounding box, represented by dashing bounding box, to the position of all objects of the same class in the current frame, represented by solid bounding boxes. Since these objects don't move much from frame to frame, I can assume they will be the objects in the current frame closest to them in the previous frame, represented by the solid red lines. But note that a new fire event has appeared. This object whose centroid has no equivalent is recorded as a new event. On the other hand, if an object disappears from view for a total of m consecutive frames, its record is removed and its numeric identifier is made available for future assignments. So number 3 for it. Now that we have tracked the fires, we can monitor the size, the area of the detected bounding box over time. If the area of the bounding box grows above a certain threshold over a time span of W frames, the fire or smoke detection is confirmed and an alarm is activated. The measure used to quantify the temporal growth rate of the detected object is the coefficient of variation. Finally, this approach allows to minimize the number of false positives, since the main agents of the false detections are static or don't show a growth trend over time, such as raindrops, car lights, solar reflections. We will see this better in the qualitative results in a moment. To train the two-dimensional convolutional network to detect fire and smoke classes, we propose the DFIRE dataset, which is available on GitHub. DFIRE contains more than 21,000 labeled images. Most of them have more than one event of a given class. So in total, there are about 12,000 bounding box labeled as smoke and more than 14,000 labeled as fire. And images were captured mainly from the internet, but also collected from fire tests, surveillance cameras, and we also made some synthetic images. A video database is also developed to test the efficiency of the proposed temporal analysis based on tracking. We collect 100 videos, 50 positive examples and 50 negative examples, most of which were taken from environmental surveillance cameras of the Put Out the Fire website, where our proposed system is running in production. And it's also available free and online. To carry out the experiments, we split the DFIRE dataset into two independent and identically distributed sets. 80% for training, more than 17,000 images, where data augmentation techniques were randomly applied during each iteration of the training, each batch, and 20% for testing, more than 4,000 images. As these deep learning algorithms contain a high number of hyperparameters for training and for inference, we have only tuned the two that most affect the performance of the detection network: learning rate and confidence threshold. Its hyperparameters for each detection network were tuned by the grid search method with 5-fold cross-validation. The implementation of this hyperparameter optimization routine is available at this GitHub repository. The other hyperparameters were kept at the full values of the original paper. After training the detection networks, we can see the performance on the test set. The first aspect here we can see is that YOLO v4 performed better than TinyYOLO v4 on all evaluated metrics. This is expected because YOLO v4 has a deeper architecture capable of extracting more refined features from images at different levels of abstraction. However, YOLO v4's better performance comes at the cost of higher training and inference computational costs. Another common aspect of the detection networks is that analyzing the average precision of the classes AP smoke and AP fire, both networks have greater difficulty in detect fire than smoke. This is because in addition to manual fire labeling being more subjective, fire events are regions with a smaller number of pixels. And algorithms like YOLO, that is single stage detectors, have some limitations with small objects. Although the mean average precision of the network is not as high as it is used to see in machine learning in general, that is values greater than 90%. In the detection problem, especially in the fire detection problem, these metrics values must be carefully analyzed. For example, intersection over union greater than 50% implies in good object locations. In addition, average precision and F1 score always penalize false negative, which is expected, but many DFIRE images have multiple fire events per scene, some really small in size. Even if failing to detect these small events affect these metrics, it may be that in a real scenario, this is not so critical. Assuming a static camera with a medium distance of the region, identify a fire or smoke event in the image may already be enough to suppress other events in the same region. So now let's go to some qualitative results. Here we can see successful detections in the test set. There are extremely small detections in low-lying environments and in early stages. But unfortunately, false positives were also recurrent. For example, raindrops and clouds confused with smoke. And that's why we introduced temporal analysis. We hope it suppresses most of these step false positives. And the most important factor of temporal analysis is the suppression threshold value. We need to tune it because high values can suppress true positives. Therefore, the best threshold will be the threshold that most suppress false positives without impacting the true positives too much. To analyze this trade-off, we use the ROC curve, considering 30% of the collected videos and a window of 20 consecutive frames. Thus, we define a threshold of 0.05 for YOLO v4 and 0.01 for the time YOLO v4. The remaining 70% of the collected videos we are using to estimate the impact of the temporal analysis on the detections made by the trained convolution networks. This network name plus acronym TA represents the network integrated with the temporal analysis. And from this table, we can see that for both networks, the temporal analysis resulted in a reduction in the false positive rate at the cost of quite a smaller reduction in the true positive rate. Suppressing detections from tiny YOLO v4 may not be very advantageous, as it significantly affects its true detections, which is already reduced by its architecture with few layers. However, for YOLO v4, we reduced 60% of the number of false positives with only a reduction of about 3% of the number of true positives. And in addition, the detection delay number of frames from our temporal analysis is pretty small for both networks. In time, we have a delay on the order of milliseconds. So concluding the presentation, in this paper we present a two-stage fire detection system, detection and temporal analysis based on tracking. We also propose DFire, a new database created for use with fire and smoke detection algorithms, which is available on GitHub for free use. We can see that integrating the temporal context as presented in this paper in deep networks allows to significantly reduce the number of false positives at the cost of a small reduction in the number of true positives. But it's not interesting for networks with few layers. And finally, we can also see that temporal analysis results in very small delay, which does not preclude real-time detection using GPUs. As future work, we plan to keep updating the DFire dataset, contributing to research in fire detection, and we also plan to create more elaborate models for the movement or temporal analysis of bounding box by treating them as time series in order to extract meaningful features about fire and smoke objects. Thanks for listening. If you want to get in touch with me, do it by email, LinkedIn, or GitHub.
Thank you, Pedro, for your presentation. We have 5 minutes for questions. Does anyone have a question for Pedro? I have a question from the chat. False positives on the test set were chosen according to the context of your application.
Yeah. We have a system called Put Out the Fire website, where my algorithm is in production, and there are surveillance cameras there, so we monitor some parks and some forests in Brazil. So we have a specific environments, and so our application is based on that these environments.
Is there another question? I was wondering about the running time. You were worried about selecting an algorithm that has a low execution time. So I was wondering how many time does it require to train your algorithm, and how many time does it require to execute it when you are seeing a new image or a new video?
Yeah, okay. Tiny YOLO v4, which is the faster version of YOLO, takes in your machine specifications, where the details is in the paper, takes about 80 hours for training its parameters and filters. And YOLO v4 takes 40 hours. So it's, and for inference, YOLO v4 with an image size of 416 takes in your machine takes 3 seconds, and Tiny YOLO v4 takes maybe a half of I don't know 0.5 seconds.
Okay, see, it's negligible.
Yeah,
Okay.
it's a big difference.
Okay. Is there any more questions? I would like to highlight that you have made your data set available. I think that that's wonderful. It's very important in our discipline, and that
Yes.
when you do a research, you make your data available for another researchers or another, I don't know, whoever wants to continue or try to work with another algorithm on your work. So I would like to thank you. Can you give the host back to Cesar, that he gave you the host to Cesar San
Okay.
Martin? Okay, thank you. Let's all thank Pedro. I don't know if when we do these virtual presentations we applause, but I will do it. Okay. And okay, the next paper that is called a hyperparameter tuning approach for shallow and deep neural network software. Fortunately, there's no one here to present it, so we are going to wait until 15 and 10 minutes for the next presentation. Is there any one of the authors of semantic expansion to improve diversity in query formulation here?
Yes, I'm here, Martin. Thank you.
Christian, from which university are you?
Universidad Austral de Chile.
Universidad Austral de Chile. So I can introduce you before your presentation. Okay,
Okay, thank you.
let's, we can wait until 10 minutes past 3, so we keep the schedule and we will listen to Christian presentations. Is there anybody here from the 4 paper, a propose of genetic operators for quantum algorithms with real representation?
I'm here.
I don't see you. Who is Eduardo Diaz?
Yes, I'm here. Can you listen to me?
Okay. Yes, I'm listening to you. From which university are you?
Instituto Federal do Rio de Janeiro. Federal Institute of Rio de Janeiro.
Federal Institute. Okay. Well, we see at in 13 minutes, we begin with the next presentation. Okay, we are back to the technical session 1. The next work is also from the Ethical, Humane and Sustainable Application of Computational Intelligence track. The work is called Semantic Expansion to Improve Diversity in Query Formulation. Paper is from Elliot Ide y Cristian Olivares Rodriguez, and it will be presented by Cristian Olivares Rodriguez from Universidad Austral de Chile. Go ahead.
Thank you. Welcome to everyone. Today I will present the work called Semantic Expansion to Improve Diversity in Query Formulation. This is a work developed by Elliot, who is a computer science student, not yet, but in this moment. Excuse me. Well, this work is talk about the search for information in the web, which is present in our daily lives. It's allow us to answer doubt or in many cases learn a lot of things. But however, we have some issues when we need to develop or to elaborate queries, because we need to properly understand the information need in order to define a proper approach to search based on our condition, in order to define a proper strategy in order to explore the web. But we require a strong vocabulary in order to develop a proper keyword selection. And also we need to decide how long are our queries and how to reformulate in order to explore the web in an efficient way. But we need to know that 75% of query correspond to reformulation, and particularly of new attempt on the same intention. So we need to know what are our needs, how to approach the search, and how to explore our proper condition in order to elaborate the queries. So we need to know also that we have two approaches in order to develop the query formulation, in order to assist to the users. The first one is query expansion, which is the incorporation of meaningful terms in order to reduce the ambiguity, and also query suggestions, which is suggest new queries in order to improve or explore in another ways the web. For instance, here we have two examples. We have the expansion, cómo construir un auto planes, which add the word planes into the query, the initial query, or suggestions, construir automóviles carreras swapbox, which reformulate or modify the initial query based on some similarities models. But here we use some relevance as a metrics, and also we know that the search engines are generalists. We have that Google or Bing are not specified for a particular domain or wherever. So the relevance is a primary factor in order to define which documents are more relevant for or more similar to a query. So the results the search results have a low diversity. And also we reach a partial vision of the information need. So this is some kind of problem because we reach some kind of bias derived from the search engines. So the proposal of this work is implement a method that delivers terms to increase the diversity of the result. So the main goals was define what is our definition of diversity, propose an expansion method, and then develop the software and test our diversity over the results. In order to do this, we use the records of and result to further satisfy the need for information. So we have an information search dataset provided by a learning platform based on information search. So, so one of the first concepts that to emerge in research is relevance, not necessarily equivalent to the frequency or novelty. So at the best, within a collection should provide finite allowed to satisfy the need, like other methods that support the formulation it arise. With intention of using the records of the results, this proposal try to locate the best or the most diverse results. So we include expansion with terms from the retrieved document qualified as relevant by the user on the system, specifically with the category of pseudo feedback, assuming the top document as relevant. So two approaches to deal with diversity arise. First, we deal with results to increase the diversity. So we can modify the order of the rank from the search results, or we can suggest query in order to improve or to move the topics of the search. Excuse me. Oh, okay. So Carbonell and Gonstein propose one of the first diversification algorithms together with the maximum marginal relevance metrics. So they propose a novel and interest algorithm in order to provide more diverse results to give a wide vision of the topics to the users, to the search users. Also, it is worth mentioning that because an external system is used, reordering is not part of this scope. So we are focused on how to modify the queries in order to improve the diversity. So we belong to the second perspective, is such as the work of Unemoto. So Unemoto support the discovery of aspects in some areas in order to improve the diversity. Referring to query expansion, they present an approach as a diversified expansion of queries. They use free semantic network, can be used for word embedding or vector representation of words containing relationship between words with containing relationship between words with a weight associated with an action or capability. So they use a thesaurus in order to improve the diversity. Another factor to consider is the source of information. So we can use several search engines or content analysis or social network in order to search information. For instance, we can use PubMed, which is specified to medicine, or we can use a more generalist search engine such as Google or Bing. So we decide to use a more generalist search engines because it's the wide use search engines by the whole world, in particular by the students. Having already a source of document associated with queries, it is necessary to define how to compare with the new ones obtained through the expansion. We need to compare the document between the documents. For this, we use with the premise that a low similarity imply low similarity of the associated query. This type of metric has been widely used in the text classification or clustering algorithm, and it's usually employed by several research. Each component indicates a document feature, such as the number of a frequency of a term. Depending on what we base the similarity on, we do compare based on the terms. So, for instance, we can use lexic semantics or semantic similarity. Here we have two similarity, the left sign and the cosine, and we can see how differ this similarity, these two similarity. And also, we can, among the alternatives, which include to find the cluster of queries or synthesize of suggestion, we focus on the integration of semantics to understand the query intention. As we mentioned above, the relevance of the result is a factor over which the system has no control. We have no control over the order of the result, just over the type of query that the user can issue. But we can quantify is whether there is a relationship between the query and its expansion. So we can compare the two queries, specifically a relationship of semantic feature properties. The problem with the representation that are only based on occurrence, such as the backwords, is that they not consider the order in which the words are written. For instance, they will have the same representation under this model, such as this little example. What is the advantage of this model? It's allowed to preserve the semantic proximity of the words, being able to find semantically similar vector close to each other in the space of future and perform some operation. In relation to the expansion, there are works that apply this model, but its emphasis is on the reordering of the word, not in the query suggestions. Now, this model has two architectures for this implementation. In both cases, is based on a neural network of one hidden layer. So our problem is based on the context where there is a notion of the search intent associated with a task. So we provide the search task to the users in order to be solved. Also, we have the query logs, which is available, and there is no control over the information retrieval system that provide the results. So we define our target problem as a recommendation task. So we need to fit the best query in order to improve the diversity over the results. So we have two research queries. The first one is semantics-based term expansion able to increase the diversity of the results? And the second one is, what is the relationship between semantic similarity and estimated diversity? So our method is based on a simple architecture where we catch the query, we define a candidate extraction. So we need to define a diversity measure. After that, we perform some pre-processing in order to define a corpus. Then we train some model of word-to-vec in order to obtain a vocabulary and provide a semantic selection. In order to do that, we perform some scrubbing using Bing, and then we perform some format and filtering of the words. After that, we develop some configuration, some setup of the model in order to evaluate the training process. And we have 3 parameters: the mean frequency, the window size, and the vector size. So with this architecture, we have 5 process phases: the pre-processing, the model training, the semantic selection, the scrubbing process, and the post-diversity measure. So we use the Gonza platform, which is a search information based of learning platform based on search information. Sorry, and we have the logs of every action of the user in this platform. So we provide the search task here, then the users can query on the web here, and then they can open some links, save some links, and finally provide some answer regarding to the goal of the task. And here they have some library of document or relevant document from this user, for each user. So here we use the definition of the problem of the search task, and every snippet obtained by the user at every query that they issue in a naturally way. So we have some query and these snippets, so we can use these words and this title here in order to train our models. From this data set, we know that there are 345 queries issued by 13 first-year engineering student in 2019, 12 queries on average by user, and just 5 unique queries in the total, in the whole dataset. The specific task with which this concept and semantic similarity is explored correspond to the challenge of building a soapbox car.
Christian, you're running out of time. Try to hurry.
Okay, so we develop some corpus. We provide some list of sentences in order to train some word-to-vec. We measure the diversity over the result of each resulting or proposed query, suggested query. And we define 3 models in order to compare which one is better than other. We use the cosine similarity in order to provide some measure of the diversity. Finally, additionally, we define two groups based on the quantity of query used, and the result for the first research question is that we improve a little bit the diversity over the result, so just suggesting new queries based on the previous one, and using the contextual information such as the problem information and also the snippet information. Here we can see some improvement of each model of the diversity regarding to the initial diversity, which is the red line. See the initial diversity or the original diversity over the result of users. And what is the relationship between semantic similarity and estimated diversity? So we also we have that similar to the case of the extremes, the distribution of diversity on model B of all the expansionist study. We have a graded deviation around the semantic similarity, and the diversity can be seen in group 1. So we can see some improvement of the diversity. So also we analyze the quantity of query the quantity of words that we can use. So we can use 0 to 10, 10 to 20, etc. And from 20, we can see some little improvement of the diversity because the words are more different than the initial ones. So possibly a possibility of the increase in the estimated diversity with the incorporation of a single terms. So we analyze just incorporating just one single term by each query. For each group model pair, there are between 43 to 58% of case with higher diversity than the original one, without the suggested term. Some questions to future work: is a lexical comparisons enough? What does a low diversity value imply? And a more deep analysis of this group of queries. So we reach some little improvement of diversity, just improving or providing a new query suggestion. We not use the rank of the results. In selection, lower semantic similarity may lead to higher diversity, and we have some first implementation over the platform. So this suggestion is running in the platform, and we need to explore another parameters of the model in order to improve this proposal. So thanks.
Thank you, Christian. Unfortunately, we have run out of time for questions. You have used it during your presentation, so I thank you. And okay, we can all thank Christian. You had to stop sharing your screen, so now we can give to the next presentation. The next paper, it's called Propose of Genetic Operators for Quantum Algorithms with Real Representation. Is from Eduardo Diaz and Marley Velasco, and the paper will be presented by Eduardo Diaz, that he is from the Federal Institute from Rio de Janeiro, Brazil. Eduardo, you can start your
Can
presentation.
you hear me? Can you hear me?
No, maybe you were mute. Start again, please.
Can you hear me now?
Yes, we can hear you.
Show. Hello, my name is Eduardo de Supoio Dias, and I will present my work called A Proposal of Genetic Operators for Quantum Algorithms with Real Representation. My advisor, Marley Velasco, helps me, and I'm glad for these opportunities to show our work. So in the literature, there are many quantum-inspired evolutionary algorithms that provide good performance and results when applied to solving sum of problems. We can find many applications as ordering, classification, numerical, and combinatorial problems. So what quantum inspiration have better than classical evolutionary algorithms? Quantum individuals can represent multiple states. So we can reduce the population size, and then we have less computational effort. In general, a quantum-inspired evolutionary algorithm has this dynamic. So first, a quantum population is created. But to evaluate the solution, we have to collapse these quantum individuals, creating a classic population. Classic population was evaluated, and this evaluation was repassed to quantum population for quantum operators. So here we have basically two different representations. First, binary representation proposed by Henneking. In this representation, we have a pair of genes, a pair of parameters, alpha and beta. Each gene is a pair. So on real representation, recommended for neuroevolution, we don't have more a qubit. We have a density probability function that say the probability that this gene collapse in a value between a lower and upper limits. Normally, the pulse quantity is used, the uniform function, as here. So for binary representation, we have key gate quantum operators. And for real representation, we have 1/5 rule. So new operators, but new operators for binary representation were created aiming better results. Muhammad created some operators to binary representation, as shown here. First, we can see 1-point crossover. So we select two individuals and cut them in the same point to combine them. We also have a 2-point crossover with the same idea. In quantum inversion mutation, we choose one gene to change alpha and beta values. These binary proposed operators increase the results until 15% in the binary representation. So if new operators increase the results in binary representation, maybe new operators for real representation can increase the results too. we developed 3 crossover and 2 mutation operators for real representation. For the crossover, we developed the 1-point and 2-point crossover with the same idea to binary representation. The third crossover operator was called quantum arithmetic crossover. The equations can see here. The mean of child is a weighted mean, and the width is arithmetic mean of parents' width. In the figure, the purple graphs is the son, and the other his parents. We also developed the CRIP mutation for real representation. Sorry. The equation can see here, the CRIP mutation. The red line shows the bare current solution, and the operator brings the solution into this direction. Another mutation operator development is a swap operator. The swap operator changed to select genes as classical operator. So we have now 6 possible combination and 150 rule, and seven possibilities. To compare them, we will optimize 4 different functions with different dimensions that can be seen here. Function F1 with dimension 3, function F2 with dimension 4, F3 with dimension 5, and F4 dimension 7. So the results can see here. For the functions F1 and F2, the results are here. The best combination is X3 M2. X3 is arithmetic crossover, and M2 is CRIP mutation. It's the same. This combination is the best in these 2 cases. For F3 and F4 functions, X3M2 is the best for F3 function, but for F4 function, X3M1 was the best combination. Ou seja, X3 arithmetic and M1 swap mutation. So for statistical comparing, we make a Friedman's rank, and the results is here, and we reject the hypothesis of equal ranks, considering a significance level of 5%. In conclusions, we have on average quantum arithmetic crossover with quantum CRIP mutation was the best combination. Relative percentage deviation equal 682%. So 1-point crossover with CRIP mutation present the smallest standard deviation, more stable combination. Quantum arithmetic crossover with swap mutation also present good performance. We see in the function 4, but combination have different performance depending on dimensions problems. To future works, we'd like to apply the proposed operators in real or simulated applications. So sorry for my English, I'm a little nervous, and I think I have some reference and thanks for watching my presentation.
Thank you, Eduardo, for your presentations. We have room for questions. Does anyone have any question for Eduardo? If you have a question, you can put it on the chat so I can read it aloud. I have one question. You work on the design on adapting some genetics operators that were proposed for the binary quantum algorithm over the real quantum evolutionary algorithm. But then when you make your analysis of the results, I, I was not able to see how the new operators of you make a fair comparison and study all the aspects of the operators, and you say, okay, this behaves good, this behaves bad, but I could not see if it was the new operators that you proposed, the ones that were on the first place of the ranking, and also how much they improve over the previous operators that were proposed in the bibliography before you make this proposal.
See, this article, binary article, show operator for Mohammed is my inspiration. So, but we have less works, few works with real representation. So it's a new representation, real. And only operator before this to real representation is this 150 rule. This operator is used to optimize real representation, real quantum, real representation, quantum population. So, and I'm questioning, I'm thinking, because crossover operator and mutation operator is the common, is the common operators for classic, for binary representation. And why in real representation we have to make different? Because it's very complicated to combine quantum populations. So, and it's a new model to combine quantum populations based on his fitness. So, can you understand? And it's new operators as versus 150 rule.
Okay. Thank you. Does anyone have another question for Eduardo? If no one has questions, so we thank Eduardo for his presentation. You can stop sharing your screen. And now it's the time for the last presentation of. I forgot to say that the work from Eduardo was from the track Evolutionary and Swarm Computation. The next work is also from this track. The work is called Towards Multi-Output Kaizen Programming Algorithm by Jimena Ferreira, Ana Inés Torres, and Martín Pedemonte. And the presentation will be done by Jimena Ferreira. So you can start sharing your screen and making your presentation. Thanks.
Thank you. Good afternoon. I'm presenting our work entitled Towards a Multi-Output Casing Programming. My presentation will cover a brief introduction to cerebral models. Then I'm going to talk about casing programming and our multi-output approach. Then I'm going to present our experimental cases and implementation, and some results and conclusions. In chemical engineering, it's usual have multi-output problems where the outlet variables share terms that reflect the physicochemical phenomena. The typical methods in machine learning, such as kriging, support vector regression, genetic programming, and casing programming, are single output solvers, with the exception of the artificial neural network, but the models obtained by this method are not easy explainable. So our goal was analyze and evaluate the performance of the multi-output casing programming and compare the performance of multi-output casing programming with the single output casing program. Surrogate models are black box models that approximate the behavior of a system with high accuracy by fitting input-output data. Casing programming is a machine learning technique that it was proposed by Veloso de Melo in 2014. It's a method that aims for a model that is a linear regression of non-linear bases, where bases are individual of genetic programming, and the coefficient beta are calculated by a linear regression, such as ordinary least square. The method starts with the generation of the initial population. Then by crossover and mutation are created the offspring, and the initial population and its offspring are combined in a expanded population. Then the beta coefficients are calculated with a linear regression of the expanded population, and then a future selection stage is occurred, and some individuals are discarded based on the p-value of its coefficient. This iterative method continues until some stopping criteria is reached. So, as example, are the number of iterations or generations, and some threshold related with the adjusted R square. In our multi-output approach, we start the algorithm in the same way as the casing programming, but in the stage of the linear regression, the method performs a multi-output regression based on ordinary least square, and in the stage of future selection, the most relevant individual for each output variable survive for the next iteration. Now I'm going to present the experimental cases and settings. In order to evaluate our multi-output approach, we worked with 3 schemes of sharing bases. The first one is where the function 2 include all the terms of function 1, the function 3 include all the terms of function 2, and the function 4 include all the terms of function 3. In the scheme 2, function 1, 2, and 3 don't share any terms, and the function 4 include all the terms of the other 3 variables. And in the third scheme, the function 1 and 2 and the function 2 and 3 share some terms. The function 1 and 3 don't share any term, and the function 4 include all the terms of the other 3 variables. So in summary, the scheme 1 is a situation of high intersection between the functions. The second scheme is a situation of low intersection between the functions, and the third is a medium intersection. As experimental cases, we worked with three expanded benchmark functions from genetic programming. The third one is the Nguyen 4, that is the function 4 in the scheme. In the function 1 and 2 in the scheme 1 share 3 terms, the function 2 and 3 share 4 terms, and the function 3 and 4 share 5 terms. In the scheme 2, function 1, 2, and 3 don't share any terms, and in the scheme 3, function 1 and 2 share 2 terms. Function 2 and 3 share 1 term that is not in function 1, and the function 4 includes all the terms. The other two functions that we worked was the Kaiser 12 and the Kaiser 15. In the table are presented each function for each scheme. We implemented the method in Python using the did package for the genetic programming operation and the scikit-learn package for the calculation of the beta coefficient, the R-square, and the root mean square error over the validation point. We used as a map operator the basic ones, the sum, the subtraction, the multiplication and division, and some other parameters as population size, initial and mass depth, and others were based on previous work. For both algorithms, we use the same parameter with the exception of the generation. We use for the single case in programming, we use 2000 generation, and for the multi-output, we use the number of the single algorithm by the number of outlet variables that in all the cases, in all the schemes are 4, so we use 8,000 generations. The training and validation sets were based on the work of Veloso de Melo and Van Hap of 2018. For the first benchmark function, we used 20 points for training set and 20 points for validation set from a random uniformly distribution between -1 and 1. And for the other two benchmark functions, we used 20 points for training set from a random uniformly distribution between -3 and 3. And for the validation set, we used 600 points evenly spaced between -3 and 3. We executed each test, that is, each search for each scheme and each benchmark function 100 times. Then we calculated each root mean square error over each validation set. And in order to answer if the error distribution of the 100 execution of each algorithm were the same, we applied the Wilcoxon sign and rank test with a confidence level of 95% over the root mean square error of the validation point. Now I'm going to present the main results. We separate our results in 3 research questions. The first one is about the numerical efficiency, and it was, is multi-output casing programming able to provide similar solutions than the single output casing program? We found that the median of the root mean square error is 0 in all single output casing programming, and in 33 out of 36 scenarios for multi-output casing programming. In the table are shown the result from the Wilcoxon test for each function, for each scheme between the both algorithms. We found that the single output casing programming generates better models than multi-output in 12 cases. Multi-output outperforms single output in 8 cases, and there are no statistical difference in the remaining 16 cases. So we found that both algorithms get good models. We also calculate the number of hits of the produced model for each algorithm. In the figure are presented the number of hits for each family of functions for each algorithm, and we label as a hit when the root mean square error was less than 10 to minus 10. So we found that multi-output phasing programming outperformed in the single output one in 5 out of 9 cases, and in the tree scheme for case 15, both algorithms present similar results, and while in the Kaiser 12 in the scheme 2 is the only scenario in which the single output is clearly superior to multi-output. Our second research question was about the function-based sharing, and it was, is multi-output phasing programming able to provide solutions that share more function bases than single output phasing programs? So to answer that, we present in this figure, the average of the common basis for the function in the scheme 3. In red are the real numbers. In blue are presented those obtained with the model from single output, and in green from the multi-output. So we found that the single output underestimates the real number of terms shared. So the blue ones are always less than the red one, and the multi-output phasing programming tends to overestimate the real number of terms shared. In our third research question, it was about the computational efficiency. Our question was, how is phasing programming execution time affected when considering multiple outputs? So in the table, I presented the mean and the median of the well clock time of execution for each function in each scheme. We found that the median of multi-output phasing programming is shorter than the single output in 6 out of 9 cases, and the mean execution time for the single output phasing programming is better than the multi-output phasing programming. So we found that the execution of one multi-output algorithm was in the execution time was very competitive with the with a multiple independent execution of a single one. So in summary, as a conclusion, we found that the models from the multi-output phasing programming are very competitive with that resulted with the single output phasing programming. And when we analyze the number of hits, the multi-output phasing programming can find better models than the single output phasing programming for the inclusion and Kaiser 12 families of functions. And finally, the runtime of multi-output is competitive with the single output one, but it has a larger variability. Thank you very much.
Thank you, Jimena, for your presentation. We have time for questions. Does anyone have any question? You can put it on the chat so I can read them. I have one question based on your results. That it seems that your proposal has a tendency to generate functions that tend to overlap the functions even when there is no overlap. Do you have an idea on how you can deal with this in your algorithm?
Yes, this mostly happens in the scheme 2 for all the for all the functions when the shared number must be 0. We now are working in a way to give some to give less restrictions to the sharing in the algorithm. This multi-output approach force to that all the functions must have the same base in the execution. So we are now working in a way to not force in every execution to have the same individuals in all iterations.
Okay. Is there another question for Jimena? If we don't have more questions, we thanks to Jimena. And we finish now with the first technical session. We'll be back in about 23 minutes at 16:30. You will join Sebastián Maldonado, that will be the host of the technical session number 3. Thank you for coming to LACCI 2021 and to the technical session 1.
Presentation.
You hear me? I'm here.
Daniel Rios, okay.
Yes.
Do you have access to this? Are you able to share your presentation?
Oh, let me see.
Great.
Okay.
Yes, we can do that. So perfect. We will start in 3 minutes. So, but I would like to start sharp on time, so there are no delays. We have the 5 presenters are supposed to be here, so we will start sharp on in 3 minutes. Okay, well, welcome everybody to this session 3 of the LACCI conference. Thank you all for staying to the very last session of the day. And my name is Sebastián Maldonado, chair of the IEEE Computational Intelligence Society in Chile, and I will be the session chair. So the first presenter is Daniel Rios Rivera, and his work is entitled Inverse Impulsive Optimal Neural Control for Complex Networks Applied to Epidemic Influenza Type A Model. This is the session. The title of the session is Ethical, Humane, and Sustainable Application of Computational Intelligence. And I remind you, please make all the questions you want using the chat of the Zoom. So, okay, Daniel, you start. I will give you 16 minutes. I will let you know when you have 3 minutes left, okay?
Okay.
Go on.
Well, thanks for introducing me. I am Daniel Rivera from Universidad de Guadalajara, and well, this is my work. The outline of the presentation is practically the same as the paper, all of the sections. We're going to start with the introduction. Well, the spread of the infectious diseases is a serious problem, and it leaves thousands of deaths every year. And influenza is one of these diseases. If we use dynamical models to model the behavior of these diseases, we can develop control theory methods that can be used to slow or eliminate the spread of the disease. On the other hand, the complex network field proposes different entities that interact with each other. And this interaction is similar to what happens in an epidemic. What this work attempts to do is that we're going to model the interaction between different populations, and in the scenario of an epidemic burst. We're going to use here, taking advantage of the complex network configuration, we're going to use pinning control, and also we're going to use neural identification for the pinned nodes. We started introducing the original seed model. This model was proposed by Kermark and McKendrick a long time ago. I think it was in the 1930s. And this model describes the behavior of a population during an epidemic.
Daniel, I'm sorry. I think you are not sharing the screen. We are just in the first screen, and it's not fully projected, so you're not moving the slides. Sorry about that.
Oh, sorry.
So we do not see the current slide.
Yes. Does it change now?
Nothing so far. I just see the first slide, but it's not full screen.
Yes.
You're using maybe 2 screens or something like that.
No, I'm not using 2 screens.
Now it's changing. Okay, now it changed, but it's still not full screen. You have to go to the bottom right and make it full screen.
Is it changing?
No.
Or no? I don't know what's happening.
Maybe you can move the slides manually as you tried later, but you should push in the bottom right should be the full screen. But I don't know. You are moving the slide and I don't see it. But just try to move the slide to the next one. That bottom is not working.
Yeah, that's what I'm selecting.
Okay. No, it's weird because you are only sharing the first screen, but you move it. I don't know if anyone has any suggestion. Maybe you can move the slide to the second slide now.
Oh, okay. So like this, you say?
Yes, you have to move it manually, and it works. Okay. We can see it's almost full screen. So continue, but focus on moving always the slide like this. Thank you.
Okay, shall I start again?
Not necessary, maybe from the outline.
Okay, so